All right, let's take a look at partial sums of geometric sequences. Take a simple geometric sequence that doubles like the one shown here, 50, 100, 200, and 400. You can calculate the total amounts as you go, called partial sums, and we use the S sub n notation for that. So you calculate the partial sums, so you go up and you look at each individual list in your sequence or each individual number, and you simply total those as you go. So the first one is 50. The second partial sum is 150 because it's the sum of the first two. So that would be 50 plus the 100, giving you the 150. Then the next one would be 350, as we're now adding three terms of the sequence together. The first three terms are 50, 100, and 200, and those three together give us that 350 total when added. And then the final sum that I'm asking you for here is the fourth partial sum, which would obviously be the sum of all the first four terms. Now, you can write these partial sums using recursive notation. So recursive notation uses S sub n and S sub n minus 1, a lot like when we did recursive notation of other sequences when we used A sub n and we used A sub n minus 1 notation. So now we're using S sub n for the notation of including the sum. So if we're going to do this, we need to think about what is the pattern doing. Well, down here I'm showing you the answer, and we can kind of think backwards when looking at the answer. We know that this sequence originally is times 2, times 2, times 2. It is doubling. So then that's where this comes in. It's times 2 times the previous term. Well, this happens to represent the previous sum. So when you do that, you're only incorporating the growth. You haven't then included the original number in your summation when you're finding this total. So you have to add on the original number. So essentially it becomes the pattern. And then once you get the pattern will be times the S sub n minus 1, because that is the previous sum. And then you also then need to just get the first number shown or the first number given, and then that goes on the end. So as you look at this, if I took this 50 times 2, then I would get equals 100, but then that's 50 short of the next sum, so then I need to add on 50. The same thing is true here. If I take this times 2, I get 300. Well, 300 isn't the next sum, it's 350, so then I need to add on the original term of the 50, and that's how it works. And then finally, you can multiply the geometric pattern here and add the first term of the sequence, is what I was showing you on that previous slide. And then try this one on your own. Try this geometric sequence. If we go from 32 to 40, 40 to 50, 50 to 62.5, we're told that it's geometric, and this only works for geometric sequences with these partial sums. We're not going to be doing this with arithmetic or any other forms of sequences, so you can learn the partial sum format of the geometrics. And so you would list out the sums, the partial sums here, and then once you get those written out, then you can start to see a pattern between the numbers. But essentially you're going to take the pattern, you're going to put it here in this blank spot, and then you're going to put your first term here so that you can calculate the proper S sub n and S sub n recursive notation of your geometric sequence.